Welcome back to the analog electronic circuits lecture series. Today is going to be lecture 14 and we are going to continue where we left off on our discussion on current sources and current mirrors. So, in the last class we looked at a basic current source. The basic current source was just the MOSFET as long as it remains in saturation. And then we said that we need to sort out a few problems. One is what is the value of this current source. So, then what did we do? We placed it around a mirror. So, I used a reference current source. The reference current source provided the value. It created the right voltage VGS for M1 such that it conducts the reference current, and then that right voltage VGS is applied across M2 across VGS of M2 to create a copy of the reference current. Now, this copy of the reference current need not be an exact copy, it could be a proportional copy. So, for example, this is 1 milliampere, this we could make 0.1 milliampere, we could make 1 milliampere, we could make 10 milliamperes, 100 milliamperes, whatever you want. Okay. So, this is as far as we had discussed. The next thing is what about its output impedance, and then we measured the output impedance of the circuit looking in from outside. The small signal output impedance of this circuit happened to be just about RDS and nothing else. Okay. A brief note, this structure is called the diode connected MOSFET. Why? Because it somewhat behaves like a diode. If you look at the VGS ID versus VGS curve, right, you are guaranteed to be in saturation, which means it is guaranteed to follow this particular curve, right, and VGS happens to be equal to VDS in this case. So, now this is a VDS equal to VGS on the x axis, on the y axis it is ID. So, this looks like the curve of a diode. So, this particular structure is also called a diode or a diode connected MOSFET. Okay. What is the impedance of this? The impedance of this is the slope of this curve, right, and what is the slope of this curve? What is the slope of this curve? This is k times VGS minus VT the whole squared. So, the slope of this curve is the same as GM. So, the conductance between these two nodes is GM, the resistance is 1 by GM. If you look at the small signal equivalent picture of this, you will see that it is not just GM, there is GM because of the current voltage controlled current source, there is also GDS because of the resistor. So, the effective impedance is GM plus GDS, the effective conductance looking into the node is 1 by the effective conductance is GM plus GDS when you look into the drain terminal, drain or gate terminal. Okay. GDS is just a small addition on top of GM. So, this analysis is more or less correct. Okay. The slope of this curve is GM, GDS is a small addition on top of it. All right. So, this is a side note, this is just for future. Diversion. All right. So, getting back to our current mirror circuit. So, we looked at two things. Number one, we looked at was value. The value is obtained from the reference. Number two, we looked at is the output impedance. The output impedance of this is nothing but RDS. Okay. Number 3 is, what is the set of voltages for which M2 remains in saturation and the device actually works like a current source. And for this we have to work out the load. So, suppose you have got a load to a voltage VDD, okay. So, VDD minus I times RL has to be more, that is VGS minus, that is VDS, that has to be more than VGS minus VT. Okay. Now, what this automatically means is that if VDD is large, then this range increases, right. I can have more I can have more RL. If VDD is fixed and RL is fixed, then I have a limited choice of the values of I. If VDD is fixed and I is fixed, then I have a limited set of values of RL for which the circuit will work as a current source. Okay. So, basically the range of voltages over here, maximum VDD is okay, minimum VGS minus VT, right. In this range it has to be there. If I increases, then RL has to be lower. If VDD increases, then very good. If VDD decreases, these have to be smaller, and so on and so forth. All right, is this understood? Okay. Now, the big question is, it is not what you see is what you get. You should be able to improve, right. So, if your boss tomorrow says that okay, I do not like an output resistance of RDS, may give me a better current source, what will you do? So, if I want to make a better current source, I have to improve upon the value of the source impedance, right. The model of the current source is like this. If I want to make the current source better, then RS has to be made higher in value for the same value of current. How will you do that? How will you get a higher impedance? By adding a common gate stage, right. A common gate stage was a current controlled current source. So, if I add a common gate stage on top of this basic current source, then what is going to happen? The output impedance that I see now is going to increase, because now the output impedance is the intrinsic gain of M3 times RDS2 plus RDS3. So, this output impedance is nothing but GM3 plus GMB3 times RDS3, this is the intrinsic gain of M3 times RDS2 plus RDS3 plus RDS2. Okay. And GM3, this intrinsic gain is large, right, it could be something like 100. If this is 100, then I have 100 times RDS2, which is much larger than RDS2, right. What about the current? The value of the current remains the same. This current continues to come out through the drain, right. There is no change in the value of the current. All that changed is that the impedance became a lot higher. So, this suddenly is a much better current mirror than our original one. All I did was added M3 in cascode. Now, if you are not, if you want to make it even better would be to add even one more device in another cascode, right. Put M4 in further cascode on top, and now you have an even higher output impedance, okay. And then you could keep going, right. This is what people used to do a long time back, right. Unfortunately, you are going to pay a price. The price is that when you add this one device on top in cascode, now the range of voltages for which it works, this range is going to become even more limited. Your swing, allowable swing on this node is more limited. Okay, we will look at that later on, but for now, do you understand that the impedance became a lot higher just by adding M3 in cascode? Okay. We already studied the cascode just by adding this common gate stage on top. I have got a much higher impedance. Great. What is the potential over here? Should it be ground? Ground is the small signal picture. In the small signal incremental picture, it should be ground, but ideally it should not be ground. It should be a value. If I put ground over here, really if I put ground, this is above ground. So, VGS is negative. So, this M3 is not going to conduct any current, and that is going to be disaster. Okay. It is not going to work if I place ground over there. Ideally, this should be some voltage which is reasonably high, such that M2 remains in saturation. M2 requires a minimum voltage. Okay, how much voltage does M2 require? It requires VGS minus VT. All right. So, this is called VGS minus VT is called VGST. All right. So, M2 requires VGST of voltage across drain to source. This node should be a voltage high enough that the voltage at the source is more than VGST. This is the minimum. The minimum voltage across the drain and source of M2 is VGST. Okay. It can be anything higher than that. So, this should be such that if I drop out one VGS, then I have at least VGST. So, this node should be VGST plus VGST of M3 plus VT of M3. So, in other words, if I assume that all these devices are identical, VT is also identical, suppose I assume, okay, then this voltage should at least be VT plus 2 times VGST, at least. Anything more than that is okay, anything more than that is okay. For example, if you know your VGST is 0.2 volts and VT is 0.5 volts, then the voltage here is 0.7, right. The minimum allowed over here is 0.2, which means that the minimum allowed over here is 0.9, but then there is no maximum, it can be anything above 0.9. Okay. If I do keep, you know, if I keep, let us say I keep it at 1.5 instead of 0.9, right, it can be anything above 0.9. Suppose I place it at 1.5, let us draw it again. So, what I have done so far is I have declared that V t is 0.5 and V g s t is 0.2. So, for all the devices. So, this particular node is at 0.7. The minimum over here is 0.2, but let us keep it at 0.8 and let us place this at 1.5, right. How I place this at 1.5 is, you do your thing, you put your resistors, do whatever you want. Place this node at 1.5 volts. Okay. So, this node is biased at 1.5 volts. Automatically, this is a small signal ground. All right. So, this is at 1.5, this is at 0.8. Now, what is the least possible voltage at the output such that both of these devices are maintained in saturation? I have fixed this at 1.5. As soon as I fix this at 1.5, by the way, this is 0.7, okay, 0.7, this is also 0.7. This device is never going to go out of saturation, this is permanently in saturation all the time, you do not have a choice. Okay. How about here? If this is at 0.8, this device is also certainly in saturation, which is fantastic. Okay. Now, if I drop the voltage over here, how low can I drop? To maintain M3 in saturation, what is the least voltage at the drain of M3? How much? 1 volt is the least. Okay. If you go below 1 volt, then what is going to happen? M3 is going to go out of saturation. Is that right? Okay. But then what is going to happen? Suppose I do go below 1 volt, what is going to happen? M3 is going to drop out of saturation, but M2 is still trying to conduct the same current, right, because M2 still has 0.7 volts across VGS, right. VDS we do not know, but hopefully let us make this 0.9, let us drop it to 0.9. Okay. When I have dropped it to 0.9, then now the VDS over here is 0.1. Okay. So, for VDS of 0.1 and VGS of so much, the current works out to something smaller than the required 1 milliampere. So, then VDS has to increase slightly, VGS has to increase slightly, right. So, let us increase the VGS a little bit, in which case instead of 0.7 VGS, I now need a little more VGS. Let us say I need 0.75 VGS, right. So, this is going to drop to 0.75. If I drop this to 0.75, this device is still in saturation. So, it is still conducting 1 milliampere. This I have given a little more margin, I have increased it to 0.75 as opposed to 0.7, and over here VDS is now 0.9 minus 0.8, so 0.15. Okay. So, they readjust. So, the source drops in voltage a little bit. So, when I decrease this below 1 volt, this source is now going to drop from 0.8, it is no longer going to be 0.8, it is going to go down, right. How much it goes down depends on these other voltages, the device parameters and so on. But M2 is still in saturation, which means that 1 milliampere is still being conducted. Okay. What about the output impedance? The quality of the output impedance has become a little worse. Why? Because this device is no longer in saturation. So, GM3 times RDS3 has dropped, the intrinsic gain of the device has dropped, right. It is no longer that large 100 number that it used to be, right. The output impedance is the intrinsic gain of M3 times RDS2, right. That is the biggest factor, right. The remaining portions are small. So, intrinsic gain of M3 times RDS2 plus RDS2 plus RDS3, right. Forget the plus portions. Intrinsic gain of M3 times RDS2. If this device drops out of saturation, then the intrinsic gain of M3 reduces, okay, substantially, which means that the output impedance of the entire circuit reduces, right. So, it will not be as large as it used to be. However, it is still conducting the same current. So, that is very nice, right. So, this degradation is very graceful, right. You will find that you can go down to 0.9, then 0.8, 0.7, 0.6, it is still going to conduct the same amount of current, right, just that the impedance now is dropping, right. The amount of incremental change that you are going to get is going to be more, the impedance, the output impedance is going to drop, but the degradation is very graceful. All right, is this understood? Okay. So, next let us see what happens if I do not place this at 1.5, if I place this exactly at, so the minimum I needed over here was 0.2. So, I want to place this exactly at 0.2 and therefore, I place the gate over here exactly at 0.9. Now, what is going to happen? The least is no longer 1 volt, the least is 0.4 volt. Now, when I drop below 0.4 volt, immediately this source is going to drop, but when this source drops, M2 no longer is in saturation, which means that this also drops out from being a current source. Okay. So, the graceful degradation is no longer there, right. The entire circuit collapses as soon as you go below 0.4 volts. All right, is this okay? So, there is some positive, some negative. You can keep this exactly at 0.9 and this exactly at 0.2, in which case you have more range. Instead of the least being 1 volt, now the least is 0.4 volts from the top. So, that is more room on the top, more headroom we call it. Okay. So, this gives me more headroom, but then as soon as it goes below this, the circuit collapses, it is no longer a current source. Whereas, in the earlier case, I kept this at 1.5 and this at 0.8. So, now the least was at 1 volt, much higher than 0.4. However, I had room, right. I had room for degradation, that is, at, if the voltage here was above 1 volt, then the output impedance would be fantastic. However, as I keep decreasing the voltage below 1 volt, the output impedance deteriorates. However, the functionality of the circuit remains, it still remains a current source. Okay. So, you have to look at the pros and cons of these. On one case you have a positive, an upside, right, that you have got graceful degradation. On the other hand, you have a downside, that the range is much more limited, right. And in this case, the upside is that the range is much more, the voltage range, the headroom is much more. However, there is no graceful degradation. As soon as you cross below 0.4, you are done for. Okay. So, these are the pros and cons. The next question would be, how do I make this 0.9 volts? And this I had, brushed aside. I said that you do whatever you want, you can place your resistors and so on and so forth and create 0.9 volts, but do not in general do whatever you want, right. There are some nice ways to generate the requisite voltage over here at the gate of M3. So, one very nice way to generate the gate voltage of M3 is as follows. Assume all the devices are identical. So, from this page what is the difference? I have added one more device on this side, on the reference side. All right. So, let us look at the reference side quickly. This is my reference current, let us say 1 milliampere. Where does it go? Does it go through this wire? No, it does not, because the gate current is 0. So, all of that current goes right through, and all of that current goes right through. This is a diode, this is yet another diode. So, I have got one diode, another diode. This voltage at, let us label the MOSFETs. Okay. So, the voltage across at the gate of M1 is just the right voltage that M2 will conduct the reference 1 milliampere. So, if this is 1 milliampere, this voltage is just correct such that the current over here is also 1 milliampere, as long as M2 remains in saturation. Okay. What about M4? What is this voltage at? This voltage is at VGST plus VT. Okay. Now, let us assume all devices have the same VGST and the same VT, in which case what is the voltage here at the gate and drain of M4? This is a diode, this is also a diode. So, the same diode drop is going to come across M4. So, this is going to be a 2 VGST plus 2 times VT. All right. Now, M3 is going to conduct 1 milliampere, the same 1 milliampere, and therefore, the gate source voltage of M3 is also VGST plus VT, which means that the voltage over here, this is 2 VGST plus 2 VT. So, what is the voltage over here? VGST plus VT. Fantastic, right? VGST plus VT. What does this mean? Is M2 in saturation or not? M2 is in saturation. Why? Because drain to source voltage is equal to VGST plus VT, which is certainly more than VGST. Okay. So, M2 is certainly in saturation, guaranteed to be in saturation. Okay. M2 is in saturation. What is the minimum voltage that you can tolerate at the drain of M3? VGST plus VT is the source of M3. So, the drain of M3 can go all the way to 2 VGST plus VT. So, as long as you are greater than this limit, then M3 is in saturation, M2 is also in saturation, right. Then if you surpass this limit, what is going to happen? This voltage is going to, the source of M3 is going to drop, it is going to drop a little. However, M2 will remain in saturation, right. So, there is this graceful degradation that is going on. You have got some room, right. the lowest possible voltage here is just VGST, but actually the voltage is VGST plus VT, which means you have got room for graceful degradation of up to VT. Now, there is one more thing to observe, one more very nice feature of this circuit, really nice feature of this circuit is as follows. This device, the MOSFET, right, the MOSFET ID is some function of VGS and VDS, all right. Now, ID1 has VGS and VDS both equal to VGST plus VT. M2 also has VGS and VDS both equal to VGST plus VT, which means that the current in M2 is exactly equal to the current in M1. They are identical because both VGS and VDS are equal in the two devices. Now, this feature was not there earlier. Earlier, whatever we did, right, here this drain was at 0.2, this drain was at 0.7. So, VDS was different, VGS was equal, but VDS was different, which means that there could be a slight difference between the actual current in M2 and the current in M1. Right. Here in the other case, VGS was 0.8, VDS was 0.8, VGS was 0.7 for M2, but in the reference device VGS and VDS are both 0.7. So, once again the currents are not exactly identical. Okay. How about in the one transistor situation? In the one transistor situation, once again in the reference VDS and VGS are equal, but in the output device VGS is something, but VDS is completely depending on the load resistor. Okay. So, VDS is totally different, which means that the current will have a lot of error. Whereas, in this case both in M1 and M2 VGS and VDS are identical, and therefore, the current is going to be exactly precisely equal. All right, is this understood? So, this is also a very nice feature. So, this particular current mirror is called the Wilson current mirror. Named after the gentleman who designed this circuit for the first time. So, this particular current mirror has one important feature, that both M1 and M2 conduct exactly the same current, unlike in the other versions. If this is 1 milliampere, this is exactly 1 milliampere. That is one important feature. Then the next important feature is that you have got graceful degradation in terms of the limit for the output voltage. The output impedance is generally very high, right, you have got a cascade. So, therefore, the output impedance is very high. However, this output impedance is going to go down, it is not going to be remain as high if you go below this limit 2 VGST plus VT, all right. The next the only problem is that this limit is fairly high, it is 2 VGST plus VT, or rather 2 VGST, this factor is extra, right, 2 VGST plus a VT. Whereas, in the optimal case I only need VGST across drain and source and another VGST across drain and source, which means that in the optimal case the lowest possible output should just be 2 VGST, right, in the optimal case. In this case it is 2 VGST plus a VT. So, the output range is suboptimal. However, it promises graceful degradation beyond the output range. So, this is a bad, then a good is graceful degradation. And then another good is high output impedance, and then another good is exact replica. All right. So, there are some good things, there is this extra cost. Okay. So, this is a very popular current mirror, it has a name, Wilson current mirror, it is used very frequently in a lot of circuits. Okay. There is an extension to the Wilson current mirror, it is called the modified Wilson current mirror, and I will briefly draw it over here, but this is a fantastic circuit and I am not going to explain how it works. Okay. So, this is called the modified Wilson current mirror. This is just an extension to the original Wilson current mirror, right. The only difference being that this connection is now on the other side. Okay. And this also behaves very similar, the performance is very similar to the original Wilson current mirror. If you look at it carefully, you have got the reference current comes right through, creates a drop across M1, right, and this is mirrored in M2, fine. But then what is this doing and what is the other one doing? Okay. So, that is just making sure that this current, this output current is equal to the reference current. So, it is mirroring this current, it is copying this current over on this side. Okay. So, anyway, so this is something that I am not going to explain right now, but this is called the modified current mirror. This you can think about it. But we are going to explain it later on. We are going to study it, just not right now. It is going to be towards the end of 2/3 of this course. Okay. So, in the first 2/3 of this course we are not going to be able to study this. We need to learn a lot more before which we can analyze this circuit. Right now I can't do it. Okay. So, these are my current mirrors. Now, if you think about it very carefully, you can add more stages, all right, and that is only going to give you more output impedance at the cost of even more limited output range. Okay, you can keep adding more stages. Okay. One popular question is, this is suboptimal in terms of output range. This Wilson current mirror is not really optimal in terms of output range. I wanted exactly 2 VGST and not 2 VGST plus a VT. Can that be arranged? Okay. And the answer is possibly we can arrange that also. It is not very difficult. However, we are going to be unable to carry on with this exact replica criteria. It is no longer going to be an exact replica, because this is now going to become 0.2, this is 0.2. Okay, so this is the basic premise. I am going to push this reference current right through this device and then mirror it and then common gate. All right. And now I have to make sure that this is at VGST, which means that this node is at 2 VGST plus VT, and the lowest this can therefore go to is at 2 VGST. This is what I have to make sure. The voltage here is VGST plus VT. Okay. So, one easy way, very easy way, is to place a resistor over here, right, of value VGST by I naught, and connect this, hook this up. So, this is now exactly VGST. So, this is 2 VGST plus VT, right, but then you need to know exactly what is VGST and what is I naught, and therefore, this resistor has limited value. All right. So, that becomes a problem. What other possibility is there? Another possibility is that, let us not bother about this. We have this MOSFET and we know that this creates a voltage over here of 2 times VGST plus 2 times VT, but I need to drop a VT below that. All right. And one easy way of doing that is to pull a large current through a MOSFET. Sorry, to push a current through a large MOSFET. Okay. So, if I push a small current through a large MOSFET, then the VGST required is going to be minimal, almost equal to 0, in which case I will just get a VT drop. All that I now have to do is pull a current through this very large MOSFET. So, you may take a very large MOSFET, W by L is very large as opposed to these 4 having equal W by L. Over here you pick W by L to be very, very large. Okay. When W by L is very large, that K factor is very large, right. If I pull the same current through it, then what is going to happen? If I pull the same current or a similar current through a very large K, then VGS minus VT the whole squared is small, which means that VGS minus VT, VGS is more or less equal to VT. So, this drop is going to be equal to a VT. All I now have to do is pull a very large current. How will you pull a very large current? I am sorry, a reasonable current, more or less equal to this. So, put another mirror over here. Coming from the same reference. All right. So, what have we done? So, this was my reference current. This is my final device. Okay. Now, I do not like this voltage. I take this voltage and I pull it down by Vt volts. And the way I do it is with the help of a device, very large device with very large W by L ratio. So, that Vgs minus Vt is almost equal to 0, which means that this is just a Vt below the voltage over here. So, all these other devices are equal in size. So, the voltage over here is Vgst plus Vt. The voltage over here is 2 times Vgst plus Vt. The voltage over here is Vgst plus Vt. This current is also Iref, more or less. Okay. It does not matter if it is a little less, it does not matter, because this device has to be large, that is all. This drop has to be Vt, which means the voltage here is Vgst 2 times Vgst plus Vt, and that automatically means that the voltage over here is Vgst, okay, which is the lower optimal limit at which this voltage can be. So, this maintains this device in saturation, and therefore, the lowest voltage that this can go to is 2 times Vgst. Okay. Is this more or less clear, this setup? So, these are all more and more optimized current mirror circuits that you can make. You can design your own current mirror circuit. I mean, you do not have to have Iref over here for that matter, right. Iref means now you have one reference current, another reference current, a third reference current, you are wasting a lot of current. So, make this L very large so that this current is very small. Okay. You need a very small current over here. So, you do not really need Iref, you can have Iref by a large factor n, right, and you will save some current, you will dissipate less current. This will still drop a Vt, and that automatically means that you will get 2 Vgst plus Vt voltage over here. Is this all right? Okay. So, we are more or less done with the current mirrors. So, these are a variety of current mirrors. Now, I want to discuss one more circuit. A lot of times people say that you want to make a reference current source. So, everywhere I have been drawing this reference current source, right. I mean all the activities are being pinned on this reference current source, everything is proportional to this reference current source. How do I make this reference current source? How do I make it? Any idea? Okay. So, what I am going to do right now is to give you some ideas to make this reference current source, and then we are going to expand on the idea and we are going to make a certain kind of a reference current source. Okay. So, this is just a general discussion, these are not real circuits. Suppose I make a current mirror that looks like this, W by L ratio is 1, W by L ratio is 1 and W by L ratio is 1 and 1. What do you think is going to happen? You have got a current mirror. Alright, by the way, I need you to now start remembering things. Okay, when you see this, what is this? This is a current mirror, current coming in over here, current being created on the other side. Alright, I need you to remember these patterns in the circuits, okay? Because when you use these, this is a block, this is a current mirror block, alright. This is also a current mirror block and you have to identify these blocks. You can't start treating every device on its own and looking at its characteristics and so on, that is no longer, I mean you are no longer in class 10, right? You are not in class 10, class 11, class 12, right? You are studying engineering, you have to move ahead. So, when you start moving ahead, you start recognizing patterns. So, this is a pattern, this circuit is a block, right? This has a pattern, this is a current mirror, right? You have to identify the current mirror and then use it accordingly in your analysis. So, if I have a circuit like this, I have got a current mirror on the bottom, a current mirror on the top. What is it doing? So, if I have a current on this branch, let us say this is I, then this current mirror, the bottom NMOS current mirror is going to reflect it and create I. And what is the PMOS current mirror going to do? It is going to reflect the I and create it on the other side, enforce it on the other side. Is this okay? It is a funny circuit, right? It is not really doing anything much. What can be a possible value of I? I could be anything, we do not know. Looking at this circuit, we do not know what is the value of I over here. All that I know is if I have a value of I over here, that is going to be mirrored and that is going to be mirrored back. What is that value? I can't tell. Okay. Let us modify this. Let us say I make this 4 times. So, 1 is to 1 and 1 is to 4. So, if I start with the current I, the NMOS mirrors it and makes it I, and then the PMOS mirrors it and makes it 4I. What is happening? Then 4I gets mirrored, right, and then the PMOS mirrors it and makes it 16I. Okay, so it is not really converging, right, the answer is not even converging, alright. So, if 16I has to be equal to I, then I must be equal to 0, okay. So, I in this case is going to be equal to 0, alright. So, I am just trying to play around over here to get you comfortable with using these current mirrors, alright. How about this? Okay. So, I have changed the circuit slightly. In fact, I have drawn it the other way. So, I have mirrored the circuit around itself, around the vertical axis. I have mirrored it. Okay. So, these are similar. This has been mirrored like this, right. So, you have got the current mirror is now on the other way, right. The PMOS current mirror is the other way. That is okay. It is nothing very significant. It is just a topological representation. But what is more important is that I have added a resistor R over here. How is this going to work? So, let us start with the PMOS. If I have some current over here I, then the current on the PMOS side is going to, on the other side is going to be 4I. This 4I current, that is the reference current, it is going to create some voltage drop VGS, right. Now, this is going to appear across the MOSFET as well as the resistor. So, I current is coming, the drop across the resistor is I times R, okay. The drop across the MOSFET is going to be the requisite VGS minus I times R, the requisite VGS for 4I minus I times R. So, the requisite VGS for 4I, VGST of 4I is going to be 2 times the VGST of I, right, because square law K times VGST squared is I. Okay. So, if I is 4 times, then VGST is 2 times. So, the requisite VGS is 2 times the VGST plus VT, and here I have got only VGST plus VT, which means that the remaining VGST is over here. So, this is just a VGST for I. Okay, which means what is I? I is VGST by R, where what is VGST? VGST is I by K square root, all right, and that gives you some current. Square root cancel out. Okay. So, square root I cancels out, and what you get is that root I is equal to 1 by R root K, or in other words I is equal to 1 by K R squared. Okay. So, this is something interesting, you are actually getting a value for a current over here as opposed to earlier. So, earlier in this case, first when everything was 1 1 1 1 you got any value, then I made this into 4, now you got a 0 value. Here you are actually getting some value now, right. So, things are getting better. Okay. So, we will proceed from here in the next class. In this class we discussed better current mirrors, current references, how you organize the bias voltages everywhere. We discussed the Wilson current mirror, and then I showed you the circuit for the modified Wilson current mirror, how in the Wilson current mirror you are getting graceful degradation. Then we even developed the circuit for optimal voltages, the best possible current mirror, but this does not create an exact replica. Okay. So, let us stop here, we will continue in the next class. Thank you.